Slack and the critical path. Slack is the amount of time by which we can delay an activity without delaying the project. After we computed the earliest start, early finish, late start, late finish, we can compute a slack for all activities in the project by computing the difference between early start and late start, or early finish and late finish. So using any of these two formulas, the difference between late start and early start, and the difference between late finish and early finish, this difference is equal to the slack, the amount of time we can delay that activity without delaying the project. And if you remember the definition of critical path is the path that consists of the critical activities such that you cannot delay those activities. They are critical. They have to be finished on time. So that means the slack for the critical path, or the activities on the critical path, which are called critical activities, is actually 0. Using slack times, or the benefit of slack times. Knowing the slack times of activities in a project would help the manager in planning the allocation of scarce resources in a more productive and efficient way. For example, if the manager knows that there are certain activities that have slacks, that means those activities can be delayed. So the manager may want to reallocate some of those resources assigned to the activities with slack times and direct and reallocate those resources to activities that have to be completed on time. They are the activities that are most susceptible to delaying the project. For example, the critical activities on the critical path, they have 0 slack times. But when we want to use the slack times, we have to be careful, because the slack times that we computed using the formula, the early start, late start, or the early finish and late finish, those actually were computed in isolation without any regard for other activities in the same path. And that's important because the activity slack times are based on the assumption that all of the activities on the same path will be started as early as possible and do not exceed their expected time. So to give you an example, suppose there are 2 activities on the same path with the same slack time. That's the total slack time for those 2 activities. That means you cannot delay both of those activities by the slack time. The total delay for those activities is the slack time that you have computed. We're going to see some examples to make this point more clear. Time cost trade-off in crashing a project. Crashing a project is shortening the duration of activities in a project that may lead to shortening the duration of the project itself. Crashing typically involves the use of additional funds to support additional personnel, or more efficient equipment, or more resources to complete the project faster. The project duration may be shortened or crashed by increasing direct expenses, thereby realizing saving in indirect project costs due to finishing the project faster. Why should we crash a project? There are many reasons to crash a project. For example, to avoid late penalties, if there exists such a penalty for not completing a project on time. So we may want to be proactive and try to finish the project earlier on. Or, for example, to take advantage of monetary incentives for timely or early finishing the project if it exists such a monetary incentives, or to freeing up resources for use on other projects. Crashing may also lead to strategic benefits by beating the competition in the market. So if we are able to complete a project faster than other people and other competitors, then That's a strategic winning point. Decision making regarding crashing a project. To make decisions concerning the crashing of a project, it would require to have information about the regular time of an activity and the crash time estimation for that activity, and also the regular cost and the crash cost estimation for an activity that we want to crash. Also, the activities that we want to crash, the list of activities that we want to crash, and that would be the list of the critical activities, the activities on the critical path, because the critical path is significant for us because that would determine the length of a project. So to crash a project, we need to crash the activity on the critical path. Critical path activities are potential candidates for crashing. If we actually do crashing on non-critical activities, that means the activities on non-critical paths, that would not lead to crashing the project or shortening the duration of the project. Here is the procedure for crashing a project. First of all, remember that you should crash the project one period at a time. If the unit of time is week, if it's day, you should crash it by 1 unit at a time. Also, crash the least expensive activity that is on the critical path. So you need to focus on the activities on the critical path because those are the activities that would indicate and would dictate the length of the project. So only try to shorten and crash those activities on the critical path. But if you have multiple options, multiple critical activities on the critical path, pick the least expensive activity to crash because you want to save money. So crash activities with the lowest crash cost. If you come to a situation when there are multiple critical passes, find the sum of crashing the least expensive activity on each critical path. If two or more critical paths share common activities, compare the least expensive cost of crashing a common activity shared by the critical passes with the sum of cost for the separate critical passes, and then pick the one that is going to cost less. So let's do an example to make this whole procedure easier to understand and follow. This graph shows the time cost balance in crashing a project. The x-axis shows the length of the project and the y-axis shows the cost of the project. The expected cost of the project is shown by this blue line. So the lengthier the completion time of the project, the costlier it becomes. So that's why we want to actually push this back. We want to reduce the length of the project, which means crashing the project. But doing so, crashing the project would actually cost us money. And suppose this line in red shows the cumulative cost of crashing. So when we want to crash the project and reduce the length of the project, it's going to cost us money. And the cost is increasing as we crash the project more and more. The cost is going to get higher and higher and higher. So that at some point, the cost of crashing is actually more than the cost of doing the project. So the cost of reducing the length is not going to actually save us money, it's going to cost us money. So we need to find a balance between these in this process. And that's actually by considering the total cost, which is shown by this dotted line here. So that's the total cost of the expected project cost and the cost of crashing the project. So the optimal point for us is at this point, which has the minimum cost. So this is the amount of crashing that we need to do. So when you want to do when you want to crash a project, you need to understand and identify the optimal point so that you wouldn't go further than that to crash the project, because the cost is going to go actually up, and it's not going to be optimal for you to do that. It's not going to be cost saving, it's going to be cost inducive and cost um, increasing to do that. So you don't have to do that. You shouldn't do that. Let's see an example of crashing a project. For the network diagram given here for this project, and also the information given in table, which are the normal time, the crash time, and the cost per day to crash each activity in the project, use this information to crash the project to save money and save time, knowing that it's going to cost $1,000 per day to work on this project. So try to work on this problem, and after you are done, come back to see the solution. So please pause now and work on this example. All right, so let's start. So the first thing that we need to do is to compute the length of the project. The length of the project is equal to the length of the critical path. So we need to find the critical path. There are only two paths here. One is A to B and B to F. So that's A, B, F. The other path is C, D, E, and F. So that's C, D, E, and F. The path ABF would take 6 plus 10 plus 2. So that's 18 days to complete. The path CDEF would take 5 plus 4 plus 9 plus 2. So that's equal to 20 days to complete. So this means that the critical path here is the longest path, so that's going to take 20 days for this project to be completed. So the length of the project is 20. So we identify the critical activities in this project. Those are the activities on the critical path, and that's C, D, E, F with the length of 20. So this is where we are going to focus on crashing the project. We're going to try to see if we can crash the activities on the critical path. That's C, D, E, and F. And we are going to actually ignore A and B because these are not the critical activities. These are not on the critical path. So crashing those or shortening the length of those activities is not going to reduce the length of the project. To crash the project, we need to crash the critical activities on the critical path. And we have several options here. We have activity C to crash, activity D, activity E, and activity F. But which of these activities should we crash? Well, to answer this question, you need to remember the time-cost balance concept. To crash each activity is going to cost us money. Although we want to crash the activity, we want to do it in a more efficient way and save money. So if you look at the table, you're going to see the last column shows the cost per day to crash. And each activity is going to take different costs to crash. For example, activity C is going to take $300 to crash 1 day. Activity D is going to cost $700 to crash 1 day. And activity E is going to cost $600 to crash or to reduce for 1 day. And F is going to cost $800. So the smart thing to do here is to list and rank these activities, the critical activities on the critical path, based on the cost per day to crash. So as we have done it in this table, we have ranked the activities from the lowest cost to the largest cause to crash. And the next question that we need to answer is, for each of these critical activities on the critical path, for how many days we can actually crash them? Well, that's based on the third column in this table. So for example, activity C, the normal time to finish this activity is 5 days, and the crash time is 4 days. That means that we can actually reduce the length of the finishing of this activity by 1 day. So that's why we have the third column here. We have 1 day to crash. Or for example, activity D, the normal time to complete this activity is 4 days. The crash time is 1 day. That means that we can finish this activity by crashing it by 1 day. So there are 3 days that can be crashed. So that's why we have activity D, we have 3 here. This is activity D. And so on and so forth. So we compute all the available days to crash for all the critical activities on the third column in this table. Now we know that for how many days we need to crash and how much we have to spend. Begin shortening the project one activity and one unit at a time, and check after each reduction to see which path is critical. Because we are reducing the length of the critical path, the path with the largest length, it might happen that another path becomes actually critical, or its length become equal to the previous critical path. So let's go ahead here and continue the process. We pick activity C for reduction because C is on the critical path. First of all, critical path has a length of 20, and activity C has, among all the critical activities, has the least cost, the smallest cost, and we can crash this activity for 1 day. So let's go ahead and do that. We're going to spend $300 and we're going to crash activity C by 1 day. So the normal time would become 4 and we spend $300. So now the length of the critical path is no longer 20. It is actually 19 because we crashed C by 1 day. So we shorten activity C by 1 day and we pay $300, but activity C can only be shortened by 1 day. So it is done. We can no longer shorten activity C anymore. So we need to look for other activities to crash. We have activity E, D, and F to crash. So we look for the one that with the smallest cost, and that's going to be activity E with $600 to crash per day. And we actually can crash activity E by 2 days. So let's go ahead and crash activity E by 1 day, paying $600. So E is going to, the normal time for activity E is going to be from 9 to 8, paying $600. So since activity E is on the critical path, shortening it would shorten the critical path. So the length of the critical path would become 1 reduced. So that's 18. So now we have actually two passes with the same length. It means we have two critical paths. So any further improvement or any further crashing of the project would require crashing both paths. So we have two passes, pass A, B, F with the length of 18 and pass C, D, F with the length of 18. So that means that we have two critical passes. So if you want to crash the project, we need to crash both of these passes. So we have listed the remaining activities of these two paths and the crashing cost. For pass ABF, activity A is not reducible or non-crashable. Activity B is going to cost $500 to crash. Activity F is going to cost $800 to crash. And for path C, D, E, F, activity C cannot be crashed. Activity D is going to cost $700 to crash. Activity E is going to cost $600 crash. And activity F is going to cost $800. So based on the idea of going with the least expense here, you might actually see that activity B with $500 and activity E here both have the least cost here. But to crash the project, we need to crash both B and E. So the cumulative cost would be $500 plus 600, and that's equal to 1100. But if you look further, you can find actually a better solution. So if we actually crash F, F exists in both passes. So if you crash it by 1 day, it's going to crash both pass ABF and CDEF. And it's going to cost $800. So by spending $800, you can crash both of these activities by 1. So that's the best way to go. We're going to go by crashing F. So we're going to crash F by 1 day, and it's going to cost $800. And we also going to have to implement this change into those passes. So by crashing F, the length of the two critical paths would become 17. Can we go any further? Because the cost of crashing B and E would be 1100 as we computed, and 1100 is more than the cost of performing the job on working on the project, $1,000. So if you want to keep working on the project, the daily cost is $1,000. So it's economically not worth it to spend $1,100 to crash the project by 1 day. So we're gonna have to stop here since F can no longer also be crashed. F only had one crash time here and we used that. So that's the end of the crashing. There's no other further improvement or other way to crash the project. So the total length of project after crashing is 70. Here is a summary of the steps that we took to crash the project. In the table below, in this table, you can see the two passes, pass ABF and pass CDEF, and also the lengths after crashing for all the steps. By default, the default is step 1, step 2, and step 3, because we crashed the project by 3 days. So at first step, the length of the critical path and the length of the project was 20. So we crashed activity C by 1 day, and the length of the project became 19. So, and it cost $300. So $300, the crashing activity was C. Next, we crashed activity E, and the length of the project became 18. So we had actually two critical paths here, and it's cost us $600, as you can see here. Since we have two critical paths now, we need to crash both passes, and we actually picked F to do that. So we crashed activity F by 1 day, and it cost us $800. So F, $800, and the length of both passes became 17, which is the length of the project. So we shrunk or shorten and crash the length of the project from 20 to 17 days. And we spent a total of $300 plus $600 plus $800, which is $1,700. So 1700 for crashing the project by 3 days, knowing that each day the project costs $1,000. So that's a total of $3,000. We spent $1,700. So we actually saved $1,300. And also what we achieved was we crashed the project by 3 days. That means that we finished the project 3 days earlier.